Thank you very much. I'm very happy to be here and grateful for the opportunity to present to you. I will talk about this work, which deals with the problem of finding ground state energies of local Hamiltonians. And, well, this is the problem. It's a central problem in physics, in many-body physics, and quantum chemistry as well. And beyond that, as we have heard this morning, Hamiltonians can express satisfiability problems and can encode quantum computations as well. So we know this problem should be generally hard. And the difficulty, of course, lies in the exponential scaling of the Hilbert space dimension with the system size. This means that beyond modest system sizes, we cannot hope to solve this problem exactly, and we need to resort to approximations. Now, the fact that the Hamiltonian that we're considering is local offers a great simplification, and it has profound consequences. It implies that we should be able to get good approximations by optimizing over a smaller subset of the entire Hilbert space, which only scales polynomially with the system size. And this understanding of this so-called corner of Hilbert space, of the states that reside there and their properties, and how to use those in practical algorithms have all been developed in the last couple of decades. And beyond ideas from quantum information theory that were instrumental for this understanding, one key idea that can be said to have initiated this whole endeavor is the renormalization group. And indeed, tensor network states, which form the backbone of the state-of-the-art algorithms that we have, are closely related to renormalization procedures. This is actually even visible from their graphical representation, but this has been noted in this paper here. And, well, this is all really great, but variational methods do not give us everything that we would like to have. They, by design or by definition, only provide us with upper bounds to the true value. And for some tasks, we also need lower bounds. For example, if you're computing variationally, or computing a state, and you would like to study the properties of that state, you also want to know that it's close to the actual ground state. So for this, you need to certify the variational outcome with a lower bound on the energy. And while lower bound methods for obtaining lower bounds exist and have been, they actually date back to the 50s, they suffer from a drawback, which is an exponential scaling of the complexity of the method in the accuracy. So they do not lead to precise lower bounds. And what I will show you today is how this idea of renormalization can be plugged into the relaxation framework, which is how we obtain usually lower bounds, to boost such computations and obtain lower bounds efficiently. Okay, so let me introduce what relaxations are and how lower bounds for many-body systems are obtained. So we take the original problem and we plug in the Hamiltonian, and we see that because of the locality of the Hamiltonian, we can express this as an optimization problem involving the reduced states on the local patches where the Hamiltonian terms act. Okay? To make sure that we get the exact answer, we also need to impose the constraint that those reduced states are compatible with some global state of the system. And to check this constraint, so if you're given a collection of reduced states on overlapping patches of the system, to decide whether they're compatible with the global state or not, this is exactly the quantum marginal problem, and it is known to be as hard as the problem that we started from. So while this reformulation didn't offer us a shortcut for a solution to the problem, it does provide us with something useful. We can now impose a less restrictive constraint, one which can hopefully also be encoded efficiently numerically. And by doing so, we enlarge the feasible set, the set over which we optimize, and therefore the minimum can only be smaller, and we will have obtained a lower bound. Okay, the picture you should have in mind is the following. So what we want to do, the exact solution would be to optimize over this set of marginals. That is the set of reduced states that are compatible with the global one. And this lies within the set of all reduced states without any restrictions except for positivity and normalization, which I omit throughout these slides. Now, the way this problem has been addressed is by these complete hierarchies. So one devises constraints of increasing complexity that, in the limit, converge to the exact. That they define sets that, in the limit n goes to infinity, recover the exact set of marginals. And now, if we want to obtain an approximation, we can impose the constraints defining, for example, this set Sn and optimize over that. And this gives us a series of increasingly tighter lower bounds. The problem is that these methods always scale exponentially in complexity. So this problem becomes exponentially large in n. Okay, and I will show you an example of such a hierarchy in a minute, and how we can use the renormalization group to overcome this problem of exponential scaling. But in terms of this picture, what our algorithm is going to do is the following. It's going to optimize over such a set, and well, what this does, it approximates the set of marginals well around the point. So for a given Hamiltonian, we will be able to get good approximations, whereas we don't care what happens everywhere else, and we can adapt this to the Hamiltonian that we're working with. And if you look at the exponentially scaling hierarchy, what I try to depict here with this picture is that it approximates the set more or less equally from both sides. That is, it would work well for two different Hamiltonians. And that's where we can save computational resources, because when solving for one Hamiltonian, we actually don't care what happens for a different one. And it turns out that this you can do in polynomial, with polynomial resources. So let me demonstrate this to you in a specific setting. So we will be working with translation invariant infinite spin chains with a nearest neighbors Hamiltonian with an interaction term h. And what we're looking for is the ground state energy density. And this is computed by optimizing over all two-body reduced density matrices under the constraint that they are compatible with the global translation invariant state. Okay, so now I will show you how this exponentially scaling hierarchy is derived in this case, and this is the locally translation invariant hierarchy. We read it in the following way. If a global state exists, then also all of its reduced states of sizes up to n exist, and they should be compatible with each other, in the sense that if I take rho m and I take the partial trace, I get rho m minus 1. So by this arrow, we mean this constraint. Because of translation invariance, it doesn't matter if I take the trace from the left or the trace from the right, I still get the same state. So that's what we mean by these constraints. And in diagrammatic notation, so the partial trace is just contracting those indices. That's how we denote it. And now that we've written down all of this sequence of constraints, we can just forget about the constraint of a global state, and we obtain a finite size problem that just involves a bunch of matrices, and we can solve it. And that's how we define the nth step in this LTI hierarchy. Okay, and this, first of all, it converges to the true value when n goes to infinity. And second, you can also see that it involves optimization over an exponentially large matrix. So we cannot do this beyond a few steps. So now, what we do, we use this as our starting point, and we will apply a renormalization procedure to this chain of states. And this is done as follows. So I will take two of such constraints. That's how they're written down in this diagrammatic notation. And now we take the first two and we apply a coarse-graining map to both sides of the equation. So it's a W2 is an isometry that maps two spins into one. It maps to a smaller system of a smaller size. Now, on the right-hand side, you see that rho 4 some of the degrees of freedom in row 4 are no longer appearing in this equation because this isometry annihilates them. So it means that we can encode the same constraint by a variable of a smaller size. And what we have achieved with this coarse graining and compression, so this we call compression, is so each one of those steps is a relaxation, and we encoded a relaxation of this constraint with smaller variables. Of course, we didn't save a lot when doing just this one step, but now we will do it through this entire chain of constraints. And to do this, we need to be careful to always express what we have on the next level. So now it's row 4 and row 5 in terms of what we did on the previous level, because we already kind of compressed this variable. And to do this, we need this condition on the coarse graining maps that we use. They need to be obtained in a iterative way. We need this condition. Then we can compress row 4 and row 5 at the same time. And if we have this condition for all m, we can do it throughout this chain up to row n, the final state that we have altogether. Now, this exactly means that our coarse graining maps form a renormalization procedure because we can add one spin at a time and coarse grain it into this system here. And there is a simple solution to this equation, and it's the following. So if we take a matrix product state as our coarse graining map by mapping from the physical indices to the bond indices, then obviously this relation is satisfied, because then we take the right and the left maps to just add one more tensor on the right or on the left, and what we obtain doesn't depend on whether we did it from the left or from the right, because it's just the same tensor A everywhere. So this gives us an ansatz for such coarse graining maps. Now, that's basically the method. I'm just summarizing how it works. We took this exponentially scaling hierarchy up to level n. It involves constraints between all the reduced states of the different sizes. Then we apply a renormalization procedure to it. As I described, we obtain a sequence of constraints that looks like this. So now it's just what I drew before, but by plugging in this MPS ansatz. And those states are now all of a fixed size. So that means that this problem now scales linearly in n. Okay? And the value that we will obtain, you see that the MPS tensor that we use for the coarse graining, it appears as a parameter in the constraints. So now the value that we will get, the lower bound that we get, depends on this tensor A that we use. And we can tune this, we can optimize those parameters to give us a tight lower bound for a given Hamiltonian. Okay, for a different Hamiltonian, it might perform poorly. So one can either do this numerically, or what we found is that there's a natural candidate for this, for such an MPS, and that is the variational ground state approximation. So the MPS approximating the ground state that we can obtain variationally from some variational algorithm can be used, can be just plugged into those constraints, and it performs surprisingly well, and that's what the results I'm going to show you now. So we did this for various strongly correlated spin models. So the Ising model, the Heisenberg model, some XXZ models, a spin 1 Heisenberg model, so it's a 3-level system, and nearest neighbors and next to nearest neighbors Heisenberg chain. Okay. So what am I showing you here in the plots? On the y-axis, it's the error of the lower bound. So the true energy minus the lower bound that we get. That's always positive. And on the x-axis, the size of the largest state that we took, the level in the hierarchy. And now, with this solid black curve, we plot the LTI result. So that's the exponentially scaling hierarchy that converges to the exact value in the limit n going to infinity. We can just compute it to n equals 13 or so. So it stops here. And now, with the different colors, we plotted our relaxation method, but for different bond dimensions. So we can choose an MPS of different bond dimensions. And it allows us to keep, the larger the bond dimension is, it allows us to keep more of the original constraints. And indeed, we see that as the bond dimension is increased from 2 to 3 to 4, our relaxation, which is always a relaxation of the LTI hierarchy, converges to the exact LTI, to the LTI result. And for values of n where we cannot compute this exact LTI hierarchy anymore, our results extrapolate this line, and they go. So we can say that the value of n for which we would have to solve the exact LTI problem, so that our outcome, our lower bound corresponds to, in this case, n equals 60. So we would never be able to solve this problem, to solve the LTI problem for such a size. And our method allows to obtain such bounds. The picture is similar for all the models. Another thing that I'm showing here is in this bar to the right. So I told you we're using an MPS to do the compression, and that MPS is obtained variationally. So it also gives us an upper bound on the energy. And that's what we plot, the error of the upper bound here from that MPS. And surprisingly, they are of a similar order of magnitude. So this means that this one MPS that we computed variationally defines both an upper bound and a lower bound that converge at the same rate. And this is rather surprising and interesting. And we don't have a full explanation. We don't have an explanation for why this is so. That's the last two models. The picture is similar. Finally, we did an efficiency analysis. So as we increase the bond dimension and n, the problem grows, but we want to see how the accuracy depends on the problem size. So we plot here the LTI hierarchy, the exponentially complex problem with the dotted lines, and you see that indeed we need to increase the number of variables in the problem exponentially to get a diminishing return in accuracy. And with our method, the trend is linear. This means that actually the resources needed for a given accuracy are polynomial in the accuracy. Okay. Finally, I've shown you an instance of a general method, which is kind of summarized in this diagram. So we had the original constraints here, and then we coarse-grained them and compressed them, and we used larger coarse-graining maps for larger states, and we obtained these the constraints that we used in the relaxation on this diagonal, and this can be formulated generally. That's what we do in the paper, and we see how we explain how this can be applied to spin systems in higher dimensions, to systems like molecules with many electrons, and to the problems of entanglement and non-locality detection in the many-body setting. This is done by formulating the appropriate marginal problem for that setting. And to conclude, well, I've shown you how the renormalization idea can be plugged into this relaxation framework and give us, well, a lower bound that can be optimized for a given Hamiltonian by choosing the renormalization procedure. And that would correspond to changing where this blue set approximates the set of marginals well. And with this, I thank you for your attention.
Awesome. Do you have any questions after that excellent talk?
Yes. Hello? Yes. Thanks a lot for the nice talk. So I think in condensed matter, people are also more, well, so the value of the energy of the ground state is important, but more importantly, they are interested in other quantities, so maybe correlation functions, or is there a gap or not? So can you obtain lower and upper bounds on other quantities for the ground state for these quantities?
So having those two bounds, having both an upper and a lower bound, allows you to have lower and upper bounds for any other local observable. And this is kind of easy to show, maybe, but I mean, yes, it's possible. I can explain maybe later.
So very nice. That's very impressive. Also, it's nice to see that your numbers that you're getting seem to be almost as accurate as the bounds from above that you have. Like it's DMRG style in the accuracy you get. But my question is there any hope of getting basically upper bounds for lower bounds, like to kind of certify how close you are with your level of your relaxation of the original hierarchy? So can you kind of get guarantees how good your approximations are?
Well, I guess one can kind of have some argument for why, because we observe a very specific slope here. So this LTI hierarchy improves like 1 over n squared, and it's pretty much accurate. Like when you fit this line. For this, I guess you can find an explanation. We didn't look for it, but I guess and then we relax that, and then I wouldn't know how to quantify how much we relax it. But we also see some. So this MPS that we use has a correlation length, and we can relate the correlation length of the MPS to the effective size that we get. So we did. So there is some scaling argument, but I don't know if we can make it into like guaranteed.
Sorry, please ignore this if you covered it already, but there's this slew of other RG-based methods, like there's ones that relate to error correction, and then these operator algebra guys like to do analytical RG-based methods. The first one, there's this experiment/theory paper out of Harvard that uses RG to help with their observables in the experiment. I was just wondering if you could comment on any relations to these other RGs.
I can't. I'm not familiar with those. I'm sorry.
In the connection to error correction, I don't know if you see. No, okay.
We can
sorry.
talk.
Yeah. Thanks.
Any other questions?
Okay, thank you. Thank you very much for the very nice talk. I was wondering that there is, in quantum chemistry, there's a similar philosophy of bounding the energy from below by doing variational RDM method. And
exactly, yes.
I was wondering how your method would compare to that one.
So it's very similar to this, right? What they do is they impose the conditions that are inherited from an n-body reduced density matrix, only in a different language. Actually, in the paper, we kind of translate reduced density matrix theory to like we describe how you would do it for reduced density matrix theory. We don't know yet exactly how to implement this, because you need to come up with a suitable coarse-graining procedure. But basically, you can do this for RDMT, and that's what I was. That's what this was referring to. So basically, you write down the sequence of these RDMT problems that correspond to larger and larger reduced density matrices, and they should satisfy conditions between them, just as the state ensemble pictured. So basically, this picture is just, you can do that there as well.
Okay, thank you.
No? Okay, very quickly.
Yeah. Okay. So a very quick question. So
Right, I don't see what.
here. So how okay, so in 2D, like the complexity would definitely be worse, but how bad would this
I don't know. We need to try. 2D has the. So if you try to use PEPs as an ansatz for the coarse graining, then you will run into the problem that basically you're mapping to a system of the size of the boundary, and that would of course still be bad. So we think that with tree tensor networks in 2D you could do it, and for this reason we also did tree tensor networks in 1D. I didn't show you, but you can do the 1D setting with tree tensor networks instead of MPS. And this was kind of meant to test the possibility of doing tree tensor networks in 2D. We still have to try to do it. I didn't work on that yet.